So we have been working with field by basis last time and converting everything to the notation of Lorentzian manifolds. And instead of the definitions we have given so far in the more mathematical part based on mostly vector fields, now we will switch to definitions based mostly on differential forms. So for example, we started to convert the vectors EA into differential forms, E subscript A. And then we will do the same with the torsion and the curvature and the connection. So for the moment we have seen how to write the metric in terms of the tetrad or Vierbein. And now we will see the torsion and the curvature. Okay, so let's start from the connection actually. So we know that we have this identity, some gamma ABC EC, and EA, EB, EC are vector fields. Then we also know that the metric compatibility condition was nabla G of X, Y, Z equals X of G, Y, Z minus G del XY Z minus G Y del X Z equals 0. So we apply that to EA, EB, EC. And see how the metric compatibility condition reads in this basis. So X is EA, the vector field that acts on the function obtained by evaluating the metric on the pair of vector fields EA, EB, EC. That's the first contribution. Then you have minus G del EA, EB, EC minus G EB del EA, EC. Okay. Well, we know that by construction, when the metric acts on the two vectors EA, EB, that's the flat space metric. So that is a constant. In the vector field is a derivation. The derivation of a constant is 0. So this goes away. And then we use the definition of those symbols gamma to compute. Here you have what? Gamma A, B, D, G, ED, EC minus G, EB, gamma, I can take gamma out, gamma A, C, D, E, D. But again, this is nothing but the flat space metric, so you have minus gamma A, B, D, eta DC minus gamma B, D, minus eta, or gamma AC d eta B d. Then let's take this, let's do the following thing. We want to switch to differential forms. So let's take gamma ABC and multiply it by the forms E sub superscript A. And that we define as omega AB. That is a one form, and so something like that in the ordinary basis. So one form, and this is called spin connection. And we want to rewrite this identity in terms of this omega, and it's sufficient to multiply everything by E superscript A. So if you multiply by that, you have EA contracted with the first index, EA contracted with the first index, and that is omega because EA is contracted with the first index. And the other two are, oh yes, the other two are, so you contract with the first index, let me call it C, and then you have AB. AB are left out. So del G equals 0 is equivalent to what? Here, by multiplying by E superscript A, you have omega dB eta dC plus omega dC eta dB. Sometimes it is convenient to raise or lower the indices A and B of omega. So basically, omega, if you raise them, is more convenient. When you raise them, omega becomes anti-symmetric. Or when you lower them, it becomes anti-symmetric. But normally we will write it one with one index, the left index up and the right index down, because it will be easier for multiplication of these objects as matrices. So these objects we will see as matrices in the space of flat indices and at the same time one forms. So when we multiply them by themselves, we have to take care of their position, not only because they are matrices, but also because they are differential forms. And again, everything we say about these flat space indices, the same way as everything we say about the space-time indices, is local. So in local coordinates, what happens when we change coordinates, we will see it probably we start today and certainly at length in the next lecture. When we will have specified that, we will know how these objects are defined on the entire manifold. For the moment, let's work locally. So the same way as we work locally with the indices mu, nu, rho, etc., we work locally with those indices. We know how to change coordinates in space-time indices. We will see how to do that with those flat indices on Monday, very probably. So torsion. Let's see how to write the torsion. Let's recall that T, X, Y. So again, we want to convert the definitions from vector fields to differential forms. These are vector fields. And so we apply that to two vector fields, EA, EB, or the basis. And that will be del EA, EB minus del EB, EA minus the commutator of EA, EB. Again, here we use the definition of gamma symbols. So this is gamma ABC EC minus gamma BAC EC. Then let's recall that we had a definition for the commutator, and we introduced certain symbols. I think they were called A. Although I see that's not strictly necessary to repeat those, so let's just copy it. Like that. So let's leave it there. EA, EB. Now we multiply by what? By the forms EA, EB divided by 2. And let's see what happens in that case. So we have EA, EB divided by 2. Then we copy gamma ABC E subscript C. But this will give the same contribution because now we have multiplied by something that's anti-symmetric in A and B. So we get a 2 there, minus EAEB. And that also gives twice the same contribution because we are multiplying by something that's anti-symmetric, so we don't need to anti-symmetrize again. Now, observe that here we have EA contracted with this index, so that gives, these are functions, these are forms, have to be careful when we move them around, but these are functions, so I can move them wherever I want. It's not a problem. So just functions. So that gives omega CB, EC, minus the forms EA wedge EB times the vector fields EA, EB. Okay, that is what we get. So the first part we will leave like that. There is a wedge EB. Yes, wedge EB. And EB remains to the right, EC. Okay, so we copy, change name of the indices for some reason, we will see, plus, minus actually, let's write those in the ordinary basis. And also for the vector fields, EA, that will be partial x rho, EB, sigma, partial x sigma. How do we simplify that? Well, remember that these matrices E are one the inverse of the other depending on where the indices are. So if you contract two space-time indices, you get a delta in flat space indices. If you contract the flat space indices, you get the metric. Okay, so what do we have here? Here we have, for example, this object and this object. You see that you are contracting A and A. So if you contract the flat space indices, one is the inverse of the other, and you have a delta. So that's omega AB, EB, EA minus delta mu rho. That means that you will have partial x mu. Okay, then, oh, by the way, there is one thing that we can actually use here, that is yes, that there is a commutator. It's not necessary to do it here. So let's copy here. Do we have another contraction? Yes, maybe. EB nu, EB sigma. However, we cannot contract here because there is a derivative acting outside. So it's better to leave it like that. So let's leave it like that. EB, EB. Then we will do something on it, but not at the moment. So you have omega AB, EB, EA minus dx mu okay, we have to do the calculation, yes. There is little we can do now, so let's do the calculation. E rho A partial rho E sigma B partial sigma, and we have two contributions. Depending on whether we move the derivative to the right or not. So one contribution will be E sigma B partial rho partial sigma. And I forgot something, now I see it. Minus, now we correct it, dx mu E rho A d rho E sigma B partial sigma. So because remember we have here the product of two vector fields, and what we should have done actually was to oh, I forgot one thing. I forgot this thing, yes. EB. Yes, so let's copy that. EB is EB nu dx nu. And there is something wrong here, that EA rho is not there. Yes, EA rho is not there, and instead you have d mu. We have contracted EA rho with EA mu. So EA rho is not there, and instead of d rho, partial rho, you have partial mu. Okay. Now it should be right, we will see it in a moment. Okay, the first contribution here, let's say this one, d mu d sigma. This is 0. Why? Well, check this. There is a contraction here of B. So this is delta nu sigma. So basically you have d mu d sigma. Actually you have dx nu, partial mu, partial nu. But the wedge makes this anti-symmetric in mu and nu, and the other is symmetric. That goes. And here we have a certain manipulation to make, which will become quite frequent, so just pay attention to this, because it's eta, let's take this factor and that factor. Here we can integrate by parts, let's say. Move the derivative to the other side. Why? Because the sum of these two things it's a matrix times the derivative of the inverse matrix. So if you move this to the right hand side, to the left hand side, you have partial mu E B nu E sigma B, which is of course 0 because this is the delta sigma nu. So if you move it to the right hand side, you have exactly the two contributions that you have, that you obtain when you apply partial mu on EB nu first, or actually EB nu second, E sigma B first, here it is, and EB nu second. So when you have two matrices that are one the inverse of the other, you can move the derivative from one to the other by changing the sign. And so let us collect the result now. What we have been writing was EA wedge EB divided by 2 times T, what was that? T, the torsion calculated on EA EB. And we found two contributions. First, this contribution omega AB EB EA. Then there is a second one here where we change the sign and move the partial derivative on EB nu. And the rest is the same. Partial sigma. Now what is this? This is now clearer to understand. Why? Because recall that this is the vector EB. This is the vector EB. And the rest, just check it, d mu e nu b dx mu dx nu, that's just the exterior derivative of EB, where EB is the form. So you have the exterior derivative of EB times EB. The exterior derivative of the form EB times the vector EA, let's call EA. And now it becomes quite interesting. So this object is a two form and a one vector, if you want. Two form and a one vector. And we define the torsion as a differential form as the coefficient of that vector, which is a matrix, d exterior derivative of EA plus omega EB EB, which will also write as covariant derivative of EA. We will define the covariant derivative on this in this new differential form approach in more generality in a moment, but for now, let's just write this definition. So the torsion is zero whenever, if and only if, this two form is zero, because it multiplies the other coefficients of the vector field. So let's say this is, you can see this object as a two form and a vector field. As a vector field, it can be expanded in a basis, like this. And it's zero if and only if its coefficients are all zero. But that means that this differential form must identically vanish. So the condition for the vanishing torsion is equivalent to the condition for the vanishing of this differential form. So from now on, this will be called torsion. These two forms will be called torsion. Okay, so now we have to do the same for the curvature. It will be a little bit longer, but it is the same. But we do it, so curvature. Let's recall the definition. R x y z equals del x del y commutator z minus del commutator of x and y z. And we want to switch from the vectors to the differential forms somehow. Okay, let's start little by little. We will get there. R EA EB EC will be del EA del EB EC minus del EB del EA EC minus del of the commutator EA EB EC. What is it? So del EA, we leave it like that. Then we use the definition of the gamma symbols. That's gamma BC D ED. Yes, minus del EB gamma ACD ED. Let's recall that we used a certain notation just to call these and if you remember del, the property of del is that del of fx is f of del x. So if you have down here a vector field multiplied by a function, the function just gets out. So these functions just get out. And you have minus a b, d, then you remain with del ed, ec. Again, this can be written in terms of the gamma symbols. Now, remember the properties of del. Again, when you act on a function times a vector, you have a contribution that is obtained by taking the function out. So del gets in, and del EA, ED is gamma AD F EF. But then there is another contribution which is obtained by acting with the vector field here on the functions. This time the functions don't get out completely, but there is an extra contribution obtained by acting by means of the vector field EA on the functions like that. Then the second contribution is the same with A and B exchanged. And the last one is what it is. So these are vector fields. But since they have two indices and they are A and B, and they are anti-symmetric, let us multiply again by EA wedge EB divided by 2. And this will become a two-form times a two-form and a vector. So we obtain this object. Observe that when you consider the first object here, if you multiply this, these are functions, so you can move them to the right, doesn't matter. But if you multiply by EA, contracting this EA, you get what we call omega. And if you multiply by EB, that one, you get another omega. So the first contribution will give omega FD omega DC EF. Probably I forgot something here. No. It's okay. With a factor 2, 1/2, but then there will be a contribution which is obtained by exchanging A and B and changing the sign. So this first contribution collects both those contributions. Then you have plus EA wedge EB. Let me copy this thing. We will study it later. And again, two contributions cancel the factor 1/2. And finally, you have minus 1/2 A EA wedge EB EF. So the first piece is already what it should be. We have to manipulate the other two now to make them appear in a better form. So let's start with the first one. EA wedge EB vector EA on gamma DBC vector ED. What is that? Well, first the forms EA mu, EB mu, dx mu, dx nu. This is EA wedge EB. Then there is the vector. The vector is EA rho, partial rho acting on those symbols gamma. That's the vector. And then we have ED. Let's leave it like that. Now let's look for contractions. This and this are contracted. And they give delta mu rho. Delta mu rho transforms partial rho into a partial mu. Partial rho and partial rho and dx mu is the exterior derivative if you place it in the right place. Oh, first I should have cancelled a little bit of things there. So here you have from this and this one and this one, you have a derivative, exterior derivative of what? Of a function, because they are acting on a function. We will arrange them. And it is to the right, to the left, because its differential dx mu is to the left, so we have to keep it to the left. Then this thing and this thing, recollect, we could have left them there, like that. ED, that's it. Now you see that this object is the spin connection, because B is contracted with B, but only gamma is under the derivative. So if we want to compute, to write this as d omega dc, we have to subtract what we get by acting with the derivative on EB also, because that's missing. So dBc dEB ED. Okay, that is it. We cannot do better than that. And now the last part. We do all this, but we will see that it is worth, because when we will get to the formula, everything will become much simpler, Bianchi identities and everything, with differential forms. So let's do something here. Minus 1/2 a mu eb nu dx mu dx nu times a d a b gamma dcf ef yeah. Well, here we have actually to go back to what it is, because this is what? Just a sec. So yes, to prove what we want to prove, we should not start from that actually. We start for something related to that. Which is this. It's related but not immediately related. So we'll see that we will get to the right expression, but it's better to start from this expression. Let's write this one in the form we can handle better. So Ea mu, Eb nu, dx mu, dx nu, and then you have the commutator, and you know how to compute the commutator. Anti-symmetrization in A and B is already there, so you have Ea rho, partial rho, Eb sigma, partial sigma, where partial is the commutator, so you differentiate the second one, and you have two contributions, which means that you lose the 1/2, because anti-symmetrization in A and B is already included into the first factor. Good, now it's easier to compute. Okay, let's see if there are contractions. There is a contraction here and here with A, so that's delta mu rho, and again this is converts partial rho into partial mu, and that again is a total and exterior derivative of what? Of E sigma B. Exterior derivative of E sigma B. Then there will be the form EB, this and this, EB, and partial sigma. And partial sigma. But let's keep the dx mu there. Dx mu. Here we can do the same trick we did before, because you see this is a matrix, this is the inverse matrix. One is under the exterior derivative, the other is not. And so d of the product is of course d of delta sigma nu, that's 0. So that means that d of E sigma b EB nu is equal to minus E sigma b d EB nu. So with that minus, here we get d E b nu and we remain with E sigma b partial rho, the partial sigma, and that is the vector EB. And there is a dx nu. Dx nu. So let us write it. This is the exterior derivative, so as a function, dx mu dx nu, and now you recognize that this is the exterior derivative of the form. So you just have this. On the other hand, with the notation we have used previously, we can say that this is those coefficients A, B, C, EC. Okay, now you have a 2 form times a vector equal to a 2 form times a vector, both expanded in the basis. The coefficients must be equal, and that is what finally gives what we want. So this thing must be equal to DE with a proper index, which is minus 1/2 EA wedge EB A ABC equals DEC. Then we will plug it in and get the final form. Let's interrupt 10 minutes.